We now introduce the first building block of deep neural nets, the multilayer perceptron or MLP. Recall that we discussed in supervised learning that given a data set, we can train a parameterized model to learn how to map the input X to output Y. As an example, we train a classifier on MNIST dataset. Basically, the classifier maps an MNIST image to a one-hot vector with size 10. Training means finding the set of parameters or data by using an optimizer like SGD. In the succeeding slides, we will formulate the function using MLP. What is function F? Most real-world problems are nonlinear. Thus, in general, F is also a nonlinear function. From a statistical point of view, F is a nonlinear function that maps the input distribution P of X to an output distribution P of Y given X. We can also say that F is an estimator of density P of Y given X. We now introduce an important theorem called general function approximator. The theorem says that any function F can be approximated by a composition of smaller functions F sub I. In deep learning, our goal is to use building blocks like MLP to compose a nonlinear function. In this slide, f of x is a composition of n smaller functions. In the succeeding slides, we will see how to represent a small function f sub I. In MLP, a function f sub I is simply linear product of weights tensor times input plus a bias tensor. Collectively, they are known as parameters or parameters theta. The overall operation is represented by linear function in PyTorch or dense in Keras. The result goes through an activation function. A nonlinear activation function introduces nonlinearity to function f. In the succeeding slides, we will discuss different activation functions. If we put many small functions in cascade, we form a model commonly known as multilayer perceptron. A function f sub I and its activation function represents a layer. A node in each layer is sometimes called a perceptron. Hence, multilayer perceptron or MLP is formed. MLP can be used as a function approximator. For example, it can be used as an image classifier. In MLP, the first layer is also known as the input layer. The last layer is known as the output layer. Everything else in between is called a hidden layer. In this slide, we expand the input layer to see its details. For simplicity, we can imagine that the input X is a 2x2 grayscale pixel. In order to process the input, we flatten it by converting it into a 1D tensor. This 1D tensor is then multiplied by a weights tensor and a bias term is added. Each circle is referred to as perceptron. The output of each perceptron individually goes through an activation function. An activation function does not have parameters. The hidden layer is pretty much the same as the input layer. The output layer is also the same, except possibly with the nature of the activation function. In this MLP classifier, the activation function is softmax. If this MLP is a binary classifier, the activation function is sigmoid. Let us examine the different activation functions. The job of the activation function is to introduce nonlinearity in each MLP layer. Without activation functions, an MLP model can only model linear functions. it will be of less utility and cannot be used for tasks such as image classification. In this slide, we introduce a rectified linear unit or ReLU. ReLU is one of the most popular activation functions in deep learning. It is characterized by its simplicity. Positive inputs go through unchanged, negative inputs are clipped to zero. The ReLU filter is shown on this slide. ReLU filter is normally used in hidden layers. Another activation function is the sigmoid function. Unlike ReLU, sigmoid is more computationally expensive to use. As mentioned earlier, sigmoid function is used in the output layer of binary classifiers. Sigmoid is not generally used in hidden layers. Other activation functions include hyperbolic tangent, which is used in signal generation such as text-to-speech. Soft loss is used in deep reinforcement learning. For classifiers, the output layer must represent its prediction using probabilities. In this case, we use the softmax function. The formula of softmax is shown. It normalizes tensor prediction into probabilities whose sum is exactly equal to 1.0. We show a tensor of size 3 with elements as shown. After going through the softmax function, the tensor elements have become probability values. Softmax reshapes the output into probabilities. Which activation to use? For the input and hidden layers, ReLU and its smoother variant called GeLU are recommended. Unlike GeLU, ReLU has sharp discontinuity as 0. Soft loss is an activation function in deep reinforcement learning. The use of activation is not mandatory for all layers. Sometimes we do not need one and we just let the tensor to pass through. For the output layer, it depends on the nature of prediction. Sigmoid is used for binary classifiers or normalized linear regression. Softmax is used for classification. Linear or pass-through is used for unnormalized linear regression. As discussed in the supervised learning video, we train our model using a loss or objective function. We may use loss functions such as MSE, MAE, categorical, and binary cross-entropy. For more details, please see our video on supervised learning. We also learned from our discussion on supervised learning that the actual learning happens when we continuously adjust the model parameters through an algorithm called optimizer. We will have a separate discussion on optimizers. For the meantime, we can use optimizers such as SGD, Adam, and AdamW. Before using an optimizer, the following steps should be done. We initialize weights with small values. Better yet, we use initializers such as Glorot or Kaiming. Biases are set to 0 or small positive values. In the end, the default MLP initializers in PyTorch or Keras are good enough. Some important data preprocessing steps to help the model converge. For input, it is recommended to normalize in the range of 0 to 1 or -1 to 1. It is also recommended to shift the mean to 0 and push the variance to 1. For output, convert numeric labels to 1-hot vectors. For linear regression, it is recommended to normalize outputs to the range of 0 to 1 or -1 to 1. We also have tunable knobs that we can adjust during training to improve the model performance. For the network architecture, we can adjust the depth to improve model performance. However, please note that there is a diminishing return in increasing the network depth. Deeper models are also more difficult to train and require more parameters and GPU memory. We can also adjust the width instead of depth. Wider models may have better performance, but they will also require more parameters and memory. For the training configuration, we can adjust the learning rate and use a learning rate scheduler that slowly decreases the learning rate with epoch. For example, we use zero point 0.1 as the starting learning rate of SGD and decrease it over epoch to 0 using a cosine learning rate scheduler. We can also adjust the batch size. Batch size is normally a power of 2. Batch size is limited by the GPU memory. Finally, we can also try using different optimizers to find the one that will enable us to achieve the smallest loss function value. In summary, we introduce the concept of function approximation. MLP is a good function approximator. MLP is one of the key building blocks of deep learning. We may also have design choices. The best way to learn how to use them is to perform actual experiments. Code demo is next. This is our MLP for CPR10 demonstration. Multilayer perceptron, or MLP, is a simple neural network model that can be used for classification. In this demo, we will train a 3-layer MLP on CPR10 dataset, and we illustrate 2 MLP implementations. The first thing that we will do is to import the required modules, and then we illustrate how to implement MLP using PyTorch and nLinear. This is the most straightforward way to implement MLP. But the most important thing to note is we must use the correct sizes. In other words, if these are the 3 layers of the MLP, the input size of the first layer, which is FC1, is exactly equal to size of the flattened input, which is 3 times 32 times 32, flattened size of the CPR10 image. The output is n hidden, which is in this case 512 by default. This becomes the input size of the second layer. In other words, we must ensure that all input-output sizes up to FC3 must fit perfectly. That's very important in MLP implementations. This is the forward method, which is called whenever the model makes prediction, the first thing it does is it flattens the input so that the input becomes a 1D. This is very important because the FC1, FC2, and FC3 can only accept 1D input. So we have here 3 implementations of flattening, and we choose the third one because this is the most intuitive. It clearly shows the actual flattening using the rearrange function. For FC1 and FC2, we use the GELU activation, and for FC3, we do not use any activation. Note that we don't need to use the softmax in this case because the softmax is already built in with the cross entropy loss function that we will use in the PyTorch model training. So we get rid of the softmax activation. Now, this is the second MLP implementation. In this case, we implement each layer using bare bones weights and biases tensors. So we create tensors for weights and biases for layer 1, for layer 2, and then for layer 3. But note that it's very important that these are bare bones tensors, so we need to initialize them. In other words, we need to implement our own initialization routine. And this is one way to initialize using K-mean initializer for weights. And we just simply zeroed the values of biases. After that, we have the forward method again, which is called whenever the model makes prediction. The same thing as the previous MLP implementation, we flatten the input, but in this case, we do the manual multiplication of the feature in the weights tensor, and then we add the bias term. And then we subject the output to JALU activation. And we do that for layer 2 as well, and then finally for layer 3, which does the prediction, again, without the softmax. Now, with those two models, we can now build our PyTorch Lightning module. And this is basically the same as the PyTorch Lightning module that we built for MNIST. All results will also be logged on 1b.ai page. One thing unique here is we have the model parameter here so that we can easily change the MLP implementation. We will also enable the training using model which is equal to ResNet 18, so we can benchmark the performance of our two MLP models. So this is the forward call, same as in MNIST, training, testing, or validation, same in MNIST. Maybe this is slightly different because we use the FAR10 instead of MNIST for the two data sets, the train and validation data sets. And then the arguments are the hyperparameters for the training. Here we train for 30 epochs and batch size of 64, learning rate of 0.001. By the way, the optimizer that we use here is Adam optimizer. Learning rates is 1 exponent minus 3. And we use cosine annealing learning rate scheduler. So we will zero the learning rate after 30 epochs. And then we train on 1 GPU. Here, we can select whether we want to train a simple MLP or the tensor MLP, or we use the for benchmarking purposes, the ResNet 18. And this is the weights and biases callback, which is the same in ResNet 18. So we will log sample input and prediction, including the ground truth. We will see this on our 1B AI page. Now, this is the actual training and validation using the trainer module. But before we call the trainer module, we instantiate the Lightning module. This is the Lightning module. And here we validate the model by simply printing the model architecture. And this is the actual training using an instance of the trainer. For this case, we'll see that the performance of MLP is about 53%. And that is for both cases. So that means our two implementation are more or less the same. Meanwhile, for ResNet 18, the accuracy is about 78%. So meaning to say our simple 3-layer MLP model is still a long way to go to achieve the performance of ResNet 18. Our MLP model, both of them have parameter count of about 1.8 million. Meanwhile, ResNet 18 has about 11 million. So you can see the difference there. So after model training, this is what you will see. After 30 epoch, we achieve accuracy about 54%. but you can see here the training loss is decreasing over equal. This is the 1B page showing the MLP training results. The first thing that we will illustrate is the simple MLP. The most important thing here is number one, the training loss is going down and the test accuracy is going up. But again, the performance is not spectacular because here the performance is only about 54%. We can also see here sample predictions given this image with ground truth of cat. The prediction is sheep, which is incorrect. This is sheep, and the prediction sheep, which is correct. This is also correct, but this is wrong, and this is correct. Primarily because the simple MLP has accuracy of 54% only. We then illustrate the result for tensor MLP without initialization. And we can see here there is no improvement in training loss, and test accuracy is just 10%, which is equivalent to random sampling. We now illustrate the tensor MLP with initialization. With this case, it exhibits the same training loss as simple MLP. It's going down, and the accuracy is also going down as the training progresses. In this case, it achieves accuracy of about 53%. Sample results are shown here. This is cat, prediction is sheep. This is sheep, prediction is truck. This is sheep, prediction is airplane. This is airplane, prediction airplane. This is frog, prediction deer, and this is frog, prediction frog. Let's take a look at ResNet 18. The main difference with ResNet 18 is the performance, as you can see, is about greater than 78%. So we can expect the prediction will be, more of them will be correct. For example, here is cat, prediction is cat, sheep, sheep. Sheep is the ground truth, prediction sheep, airplane, airplane, frog, but this one is incorrect, it's deer. This is input frog and prediction is frog. That's it. Thank you for listening.